Hello, my name is Mama the Mummy, and I'm going to teach you about gases and the kinetic molecular theory. First, we are going to talk about how pressure works. Pressure is the force exerted per unit area by gas molecules as they strike the surfaces around them. In other words, the constant force on the surfaces exposed to any gas. Pressure can be measured in atmospheres, pascals, kilopascals, torr, millimeters of mercury, and many other units. The total pressure exerted by a gas depends on many factors. For one, the concentration of gas molecules in a sample affects the pressure. The higher the concentration, the greater the pressure. Another one is volume. If the volume of the container were to increase, the pressure would decrease due to a lower concentration. The three simple gas laws are Boyle's, Charles, and Avogadro's laws. Boyle's law deals with volume and pressure. Volume and pressure have an inverse relationship. As one increases, the other decreases. For example, if you had a box of air and you decrease the volume of the box, the pressure would increase due to more collisions with the container wall. We can see this in Boyle's law's equation as P1V1 equals P2V2. Charles's law compares volume and temperature. Volume and temperature have a direct relationship. As one increases, the other increases. Let's take our box of air again. As the temperature increases, the molecules move faster and have more frequent collisions. In order for the pressure to remain constant, the volume of the container would need to increase. We can see this in Charles' equation as V1 over T1 equals V2 over T2. Avogadro's law deals with volume and amount in moles. Volume and amount are directly related, as long as the pressure and temperature of the gas are constant. If we have our box of air, we can see that if we increase the number of moles of the gas in the container, that the volume would have to increase as well to maintain the pressure of the container. We can see this in Avogadro's equation as V1 over N1 equals V2 over N2. What is an ideal gas? An ideal gas follows a few simple rules called the kinetic molecular theory. This theory uses an ideal gas as its model. The kinetic molecular theory states, particles of matter are always in motion, the volume of the particles is zero, collisions with the container wall causes the pressure exerted by gas, particles have no attraction to each other, and the average kinetic energy is proportional to Kelvin temperature of a gas. The size of a particle is negligibly small. The kinetic molecular theory assumes that the particles do not occupy any volume even though they have mass. This is justified by comparing the very, very small gas molecules to the large space between them. The collision of one particle with another is completely elastic. This means that energy is exchanged but never lost. They have no stickiness. The average kinetic energy of a particle is proportional to the temperature in kelvins. Thermal energy is distributed among the atoms, causing them to move faster. Note that we are talking about kinetic energy, not velocity. Two different samples of a gas at the same temperature would have the same kinetic energy, but the lighter of the two gases would have the higher velocity. The ideal gas law sums up all of the simple laws we just talked about into one law, which is PV equals nRT. As you may have noticed, we have not talked about R yet. R is the gas constant, and its value is equal to 0.0821 atm liters per mole K. This is a sample problem using the ideal gas law. As you can see, I converted my millimeters of mercury to atm and converted my temperature in Celsius to Kelvin. Then I plugged it into the ideal gas law equation and found my amount of moles. STP. This stands for standard temperature and pressure. Standard temperature is at 0 degrees Celsius or 273 Kelvin. Standard pressure is at 1 atm. The molar volume is the volume occupied by 1 mole of gas. The density of a gas can be calculated by dividing the molar mass by its molar volume. The molar volume at STP is 22.4 liters. Density can also be found using the density equation D equals PM over RT. As you can see, the density equation could be rearranged to be able to find the molar mass of a gas. A lot of gas samples are not pure samples, but are mixtures of different gases. For example, air contains nitrogen, oxygen, argon, carbon dioxide, and a few other gases. Since each of the components of an ideal gas mixture act independently and do not interact, each of the components has their own partial pressure. Partial pressure can be calculated using Dalton's law of partial pressures. P total equals PA, PB plus PC, and so on. As you can see in this question, it gave me the total pressure of the container, and then it gave me the partial pressures of these two gases, and then I subtracted and found the partial pressure of nitrogen. Another partial pressure equation uses the mole fraction. To calculate the partial pressure, you multiply the total pressure by the mole fraction. To calculate the mole fraction, you divide the moles of that particular component by the total amount of moles. As you can see in this equation, it gave me the separate amount of moles for each of these gases, and then I found the mole fraction by taking the moles of oxygen and dividing it by the total amount of moles. I then multiplied this by the total pressure and found my partial pressure of oxygen. According to the kinetic molecular theory, particles of different masses have the same kinetic energy at the same temperature. However, in a mixture of gas, the lighter particles will move faster than the heavier ones. The root mean square velocity is equal to the square root of 3RT over molar mass, where the root mean square velocity is proportional to the temperature in kelvins and inversely proportional to the molar mass of the particles. We can see in this diagram that the lighter molecules are moving faster and the heavier molecules are not moving as fast. Well, that's all for today. I hope you enjoyed your lesson on gases and the kinetic molecular theory.